Hello students, welcome to the class. So in this lecture, we'll focus on section 8.7 to 8.7.3 of NCERT Chapter 8, Organic Chemistry, some basic principle and techniques. This is disclaimer. Now, once you have attended this lecture, you will be able to understand the concept of organic reaction mechanism. So, there are many key concepts related to this organic reaction and those are very important to understand. So, basically, various participants are present in a reaction and you should be able to identify that what is the role of each and every participant. Now, according to the NCERT, the first section that we will be covering is 8.7 Fundamental Concepts in Organic Reaction Mechanism. In that, we will see fusion of a covalent bond, then substrate and reagent, and lastly 8.7.3 Electron movement in organic reaction. So let's start with the general organic reaction. Here I will give you a scheme that will be representing the transformation of reactant to product. By looking at this image, you can identify various parts of the reaction. We started with the organic molecule named as substrate. Then there is an attacking reagent on the arrow. This converts your organic molecule into intermediate, which further is converted into products and byproducts. Here, what is your substrate? So, substrate is a type of reactant which is reacting with an attacking reagent. Now, how you will identify this substrate? So, that is very crucial to understand. The second thing you should know about a reaction, that what intermediate is formed during the reaction. And the third thing, which is the most important one, is deciding the product and the byproduct. Whenever you do a reaction, most of the time you will get byproducts along with the main target molecule. You should be able to identify that which of these is the major product and which of the obtained product is a byproduct or a minor one. Now, talking about the key aspects of organic reactions, we have substrate and reagent. Now, whenever this substrate and reagent reacts, we often see breaking and making of bond. But that breaking of bond can also be done in various patterns. We will understand about them through fusion of a covalent bond. Third thing is, substrate and reagent can be classified as electrophiles and nucleophiles. Okay, so either your substrate can be a electrophile or nucleophile, or your reagent can be a substrate, can be a nucleophile or electrophile respectively. So this is very important to understand which one is the electrophile and which one is the nucleophile for facilitating the reaction further. Then after, if you are breaking a bond and your nucleophile and electrophile are reacting while this breaking a bond, you must know that what is the movement of electrons. Okay, how is the electron moving during the fusion of bond? To which atom the electron is going more, or is it going symmetrically or unsymmetrically? So those things are important to understand. Let us first start with substrate and reagent. Talking about substrate, so substrate is the molecule which provides the carbon atoms for the new bond formation. So this is a general statement. There can be cases where your reagent can also supply carbon, but still you will be able to identify in most of the cases that what is the substrate. But in general, it is seen that the substrate is the molecule that provides the carbon atom for the new bond formation. Then what is the role of reagent? So here you can see a reaction where your carbon source is coming from ethene, so it will be taken under your substrate category. Whereas the Br2, which is not donating any carbon, instead of that, it is donating bromine. Or you can say it is adding a group onto this substrate to give you the product. Here in this reaction, you cannot notice a byproduct. So there are reactions where byproducts are there, and there are reactions where byproducts are not present. So both cases can be possible. If I talk about the reagent, then the other reactant, which is not the primary source of your carbon atom, is taken as your reagent. Okay. In most of the cases, you will see that the reagent is the one which is either introducing your functional group or it is transforming the previous functional group to a new one. So, in your class 11th and 12th, the main focus is on functional group transformation or functional group introduction. The substance on which the functional group is introduced or on which the functional group is transformed is taken as substrate, and the reactant which is responsible for the transformation of functional group or for the introduction of functional group is taken as your reagent. So you can say that reagent is a substance that is used to bring about a chemical reaction, okay, because it is changing the functional group or either it is introducing the functional group. Like in the given example, it is introducing bromine in the ethene molecule. The question arises, what will happen in the case where both the substrate and reagent are donating carbons? How you will decide the substrate in that case? If you look at the reaction carefully, you will observe that the supply of carbon is arbitrary. Arbitrary means it changes from reaction to reaction, or it depends upon the reaction on which you are looking upon. Okay, so if both the reactants are giving the carbon, then the choice of substrate is arbitrary. You can think of it in a way that which molecule is in the focus of attention, right? So basically you will see that in generally that the one which is a focus of attention is having a greater number of carbon as compared to the one which is kind of acting as a reagent. So the basic thing is that generally your carbon source is coming from substrate. If it is coming from both substrate and reagent, then you will observe that which of the two reactant is the force of attention, or you can say it in simpler terms, or in most of the cases, that which one is supplying the most number of carbons. So this is basically your way to choose substrate and reagent. Now moving on to the next one. Of course, when you are doing a reaction, and if you are doing it for the covalent compound, then covalent bonds will be formed and they will be broken. Okay. Now you will talk about them, this breaking of bond or this fusion of covalent bond, on the basis of the pattern in which they are getting cleaved. Now, if I define it simply, fission, so it is breaking of a covalent bond where electrons are shared between the atoms. So the unsymmetrical pattern or the symmetrical pattern you will see is coming on the basis of electron distribution after the fusion. Now this pattern can be of two ways. First one is homolytic fusion. You can simply remember homolytic fusion as symmetrical fusion. Okay, means the electron is distributed symmetrically after the breaking of bond. The second one is heterolytic fusion, in which the electrons are distributed unsymmetrically, right? So one would get more number of electron and the other would get lesser number of electrons. Now we will talk about each of them and see the results of this different fusion type. Starting with the homolytic fusion. So homolytic fusion is the breaking of covalent bond where each atom receives one electron. You know it that a bond constitutes generally of two electrons, and when you break the bond homolytically, the electrons are distributed symmetrically, means the participating atoms of the bond gets one electron each from the shared pair. Now you can understand the same thing with the help of an example. Here we have a alkyl halide, so we are representing it as Rx. X is your halogen, R is your alkyl group. When you break the bond, one of the electron of the bond is going on to your halogen and the other one is going on to the alkyl chain. To do that, we are using heat or light. Now, why I am telling you this reaction? You will see this reaction in the upcoming lectures where you will notice how do we do reactions on haloalkanes. So, there is a group called haloalkanes where the carbon is connected to halogen. You call it as haloalkanes or alkyl halides. Now, coming back to the topic, you can see a name written here which is alkyl free radical. So, this is our next point of discussion. So, what are the key points that you can derive from here? The first thing is that the bond is broken homolytically because each of the species is getting one electron each. You can call this as homolysis also. Since the electron distribution is done in equal manner, so you call it as symmetrical cleavage of bond, where your each atom is getting one electron from the shared pair. So shared pair means the bonded pair is called as the shared pair. Then after the reaction, the intermediate that we are getting is your alkyl free radical. So this species is called as the intermediate. This is not your final product, of course, but it is formed during the transition of a reactant onto the product. So that is the reason we call it as intermediate. So this is the first intermediate known as alkyl free radical. Now we will talk about this alkyl free radical. So what are free radicals? The species with an unpaired valence electron. You know it very well. When two electrons are present in the same orbital, we call them as paired electron. But if a carbon species or any other atom is carrying an unpaired electron, means its orbital is having a single electron, in that case we call that species as radical. So radical is basically a terminology also in normal dictionary which is used for reactive, or you can say means unorganized thing, right? So radical can be relevant in the same way, means it has a literal sense in this use, where it is named as radical because the species is very much reactive. We'll see it onto it. And the reason is very obvious, because here we are kind of playing with the octet of the carbon. We are debarring the carbon from its previous stable octet state. But one thing is very important. Although they are present in an unstable state, they are neutral still, because the electrons that they are receiving or that they are losing were a part of the carbon. Okay, so the electron which is being lost was not the part of the carbon. The electron which is received by the carbon is a part of the carbon in the initial phase. The lost electron was a part of the other species or other carbon. So that species is also not getting charged. So remember this very important point. Your radical are always a neutral species. Now your radical can be further classified on the basis of carbon atom attached to the radical carbon. For example, if I talk about those three types, then the first one is primary radical, where your carbon is attached only to one other species. Okay, so you can see here the carbon is attached to CH2 and CH3 only. So the first type of radical carbon is primary radical. Here you can see that the CH2 carbon is attached only to a methyl group, and it has one less valency than the complete octet carbon, right? So that is the reason it is having a radical upon it, and since it is attached to only one carbon, it is named as primary radical. If you look upon to the second one, then the second carbon is attached to two other methyl groups. Okay, so two carbons are attached to the radical carbon, so it is a secondary radical. In the third case, your carbon is attached to three methyl groups, means the radical containing carbon is attached to three methyl groups. As a result, we call it as tertiary radical. Okay, so this is the way of classifying your free radical. Now moving on further, we will look upon other aspects of the free radical, which is stability and reactivity of free radical. As I told you that radical has a literal meaning, and as a result of it, free radical are very unstable or highly unstable and reactive at the same time. The reason is the incomplete octet of carbon. Now, although it is unstable, they can be stabilized to a small extent by introduction of some groups. Like if you introduce alkyl group, more and more alkyl group to the radical carbon, it will be stabilized due to the donation of electron density onto your carbon. See, the carbon that is a radical is having a shortage of electron. But if you attach methyl groups to it, then the carbon which is having a shortage of electron can get an electron density from those alkyl groups and hence can be stabilized in a way. So if that is true, we can have a order of stability. So the first one is the most stable one, which is your tertiary carbon. So I told you tertiary carbon are those which are attached to 3 carbons, and since it is a radical, so tertiary radical. Now this one is the most stable one because it has 3 methyl groups which can stabilize the carbon with a shortage of electron. Then the next unstable one is your secondary radical, where your carbon which is having a shortage of electron has 2 alkyl groups attached to it. The last one is the most unstable one, where only one carbon is attached to the radical carbon. So you must remember this series. The tertiary radical is the most stable one, then comes your secondary, and third comes your primary. Now we can have a different aspect to explain the stability of this radical. That aspect is your steric hindrance. So if 3 alkyl groups are attached onto the carbon, in a way they are prohibiting any other species to react with the carbon. So this is making the radical less reactive. Okay, so you can think of it in this way also. So to justify it more, we can take the primary center, where your radical carbon is crowded by 2 hydrogens and 1 alkyl group, whereas your tertiary carbon is crowded by 3 alkyl groups. You know it very well that the size of the alkyl group is bigger than the hydrogen. As a result of that, the reach of any other species to react with this radical decreases due to the steric hindrance. Therefore, tertiary is the most reactive one, then the secondary, and then the primary. So reactivity and stability series are same. Now moving on to the next type of fission. So we understood the pattern of fission and what are the outcomes of that fission. Now you will see the heterolytic fission. In this type of fission, your covalent bond is broken in such a way that the electrons are moved on to more electronegative element due to greater electron pull from that particular species. As a result of this reaction, or you can say as a result of this fission, we get 2 ions. The first one is carbocation. You can see this is the example that your CH3 is getting a positive charge because the electron is lost from it and that is moved on to the bromine, which is making a Br negative and a methyl carbocation. But suppose that same electron is not moved on to the other atom but onto the carbon. So that will result in a negative charge onto the carbon. Okay, and a positive charge onto the other species. What is the reason of this unsymmetrical distribution? The reason is your higher electronegativity of bromine. Now you may ask that why don't we see the same outcome in case of the previous alkyl halide? So that was also having an unsymmetrical kind of electron density distribution because halogen is more electronegative. The reason lies in the way of breaking it. Here we must be using a different condition. There we were using the heat and light. Most probably you will be using a polar condition to break the bond in heterolytic fashion. Okay. Therefore, you can say that the heterolytic and homolytic fusion is kind of dependent upon the atoms whose fusion is taking place. But still, the conditions are also very important, and that can be seen in this case clearly. Okay, the same alkyl halide can undergo a homolytic fusion and a heterolytic fusion as well. Now, the species that are formed are carbocation and carboanion. So, if the carbon gets the negative the electron, it is forming carbanion, and if it is losing the electron, it is forming carbocation. We will study about each of them one by one, starting from carbocation. How do we characterize a carbocation? It's very simple. If you see a positive charge on the carbon due to one less electron, then you call that carbon as carbocation. And it will have only 6 valence electron. Okay. Yes, there will be electrons, but those electrons will be a part of other atom. But if I talk about carbon specifically, so its own electron will be reduced to 6. Now, talking about the electronic structure of carbon, so carbon will have only 6 valence electron. Okay. So, you know it very well that it has 4 in total. 4 were coming from other atoms, but that will result into 8 electrons. At the last, you are removing 2 electrons from it, so that is resulting in 6 valence electron. So, the carbon is getting a positive charge. The question may arise, why sir? Why are we telling it as positive species? Now, it has a greater number of electrons than the previous one, but that is in relation to your whole molecule. So, your molecule is there, your other atoms are present, protons are present for the other atom as well. But the counterpart of the carbon proton is not present. Okay, you got it? And as a result of this, your carbon is getting a positive charge. You can understand this in a way. Take CH3 for example. How many number of protons it has? So, 4 number of protons. If I talk about 4 not, it will be so hydrogen, helium, lithium, beryllium, boron, carbon. 6 protons carbon has. Okay, and 3 are coming from hydrogen. So 6 plus 3, 9 protons in total. Now, what are the number of electrons? 3 are coming from hydrogen. Okay, and if I talk about carbon, what are the number of the electrons are coming from carbon? Instead of 6, it is 5 because 1 is being removed. So there will be total of 8 electrons in this whole CH3 species and 9 protons in this whole CH3 species. As a result of this extra proton, it is getting a positive charge. Okay, but if I talk specifically about carbon, then the valence shell of the carbon is now having 6 valence electron, which is coming from hydrogen and from carbon itself. The result of this unsymmetrical distribution, the bromine is getting the negative charge because of its higher electronegativity than carbon, and the bond pair is withdrawn by the bromine. Now, how do we name it? So, it's very simple. If you are talking about this methyl, so it is having a positive charge, so methyl cation. If similarly, if you take a ethane with a positive charge, I would not say ethane, I would say 2 carbon with a positive charge, then you will call it as ethyl cation. Okay, so similarly you can have propyl cation and so on. Now, what about the shape of this CH3 plus? You know it very well. Initially, if you talk about simple CH3Br, then it will have a tetrahedral structure, but after the loss of this electron, your shape will be changed to trigonal planar. So it will look like this. So 3 hydrogens will be present on the vertices of the triangle, and this carbon will be present in the centroid. Now, your carbocation can also be classified further. You know it very well that radical was classified on the basis of carbon attached to the radical species. Similarly, the number of carbon attached to this positive charge containing carbon is the deciding factor for the classification. Starting with the primary carbocation, so it will have a CH3CH2 plus example where the positive charge containing carbon has only one carbon attached to it directly. Similarly, in the secondary carbocation, there are two methyl groups, or you can say two carbons attached to the positive charge containing carbon. And in the case of tertiary carbocation, three carbons are attached to the positive charge containing carbon. Okay, therefore they are classified as primary, secondary, and tertiary. Next is the stability of carbocation. Similar to your radical, carbocations are also highly unstable and reactive species. Again, the reason is same. It is having a positive charge. First of all, it is having a lack of octet also. So both factors are kind of making the species unstable. You know it usually. Neutral species are more stable. So you can say in a way also that radical are more stable than this carbocation. But we will talk about them later. So we will not conclude this thing. It is not a final statement, I would say. There are cases where the stability order can change. Then after, similar to the radical group, alkyl groups also stabilize the carbocation as well. And the same reason, more and more number of methyl alkyl groups will be donating more and more electron density onto the electron deficient carbon. And the reason is called as inductive and hyperconjugation effect. So this donation of electron is done in various ways. So these are called as electronic effect. We'll talk about them, both of them, inductive and hyperconjugation. So they are a way to donate electron. The alkyl groups do donate electron. One thing is for sure, but there are several ways to do it. We'll talk about them through inductive and hyperconjugation effect. So if that statement is true, that more number of alkyl groups will stabilize the positive charge, that means the most stable is the tertiary carbocation, then the secondary, then the primary, and lastly the carbon which is attached to no other carbon is the least stable carbocation. So this is your order. Moving on to carboanion. We have talked about carbocation. So you will try to apply a logic onto it and see that what is the stability for carboanion. So we'll talk about them in the upcoming slide, but you can think about it. Okay. Of course, your carbon containing negative charge is named as carboanion, and in this case you will have a less electronegative element as compared to carbon, and as a result your carbon will get a negative charge. So carbon will be more electronegative than Z. As a result of that, the carbon will attract the bonded pair of electrons and will form a methyl anion. Okay, similar to the cation, you can name them as methyl anion, propyl anion, N-propyl anion, I would say, ethyl anion, and so on. What about the structure? So here the steric number would remain same in case of anion. Okay, because in the case of carbocation, the steric number is decreasing, but here it will remain same. But there will be a distortion, a higher distortion, I would say. So a tetrahedral is never perfect in case of such a group where three groups are different and one is different, as in the case of CH3Z. So three hydrogens are there and one Z is present. So of course it is a distorted tetrahedral, not accurate one. But if you are converting into a carboanion, then the distortion increases. You can see here the structure of this carboanion. So the negative charge is present as one lobe, or you can say as one arm of this tetrahedral, and the other three groups are making the triangle. Okay, so this is your shape for carboanion. So it's very important to remember these shapes, whether the carbocation or the carboanion, right? Now if you remember the previous diagram, In the carbocation, two lobes were present, okay, that were present on equatorial positions. So that lobe were a part of the p orbital. I would force you to think about that what is this lobe? It is a hybridized orbital lobe, or is it a pure orbital lobe? So I am leaving this thought onto you. Moving on to the next, we have classification of carbanion. So similarly, on the basis of carbon attached to the negatively charged carbon, we can have three different classification. If one group is attached to the carbon, we call it as primary carbanion. If the negative charge containing carbon has two groups attached to it, is secondary carbanion. If three groups are attached to the negatively charged carbon, we call it as tertiary carbanion. If I talk about the stability, so I told you to think about the stability. The stability order is reversed in case of carbanion. In case of carbocation and primary, in case of radical, the tertiary was the most stable, then comes your secondary, and lastly your primary. But in case of carbanion, the stability order is more for primary, then less for secondary, and least for tertiary. The reason is that here we do not need electron density. So if you attach more and more carbon groups onto this already negative charge containing carbon, it will destabilize it by increasing the amount of negative charge. So this is very important to remember. Now I told you that initially you have a substrate at a reagent, and either substrate can act as a nucleophile or your reagent can act as a nucleophile, and the corresponding part will be acting as an electrophile. But what are these? What are electrophiles and nucleophiles? We'll talk about them. So here I have a table to represent this whole thing. You can understand it in a simple way that electrophile are those species which are electron loving, okay, which have a lack of electron or which has a thrust for electron. Opposite to that, the nucleophiles are nucleus loving, or you can say they are attracted to more and more positive charge. What is the reason? The reason is very obvious. It must be having a higher electron density onto it. So the first thing you should remember, electrophile means electron loving because of the electron deficiency. Nucleophile is nucleus loving because of the electron richness. It is attracted to the positive charge. Now, if it is electron loving, then what it will do? It will accept electron from others. Whereas your nucleus loving will donate electrons to other because it is rich in electron. Then what about the charge? Generally, it is seen that electrophiles are having a positive charge. So if you ever see a positively charged species, the chance is that it will act as an electrophile. Similarly, if it is there is a negative charge on any species, it will act as a nucleophile. But what about neutral species? How they can be classified into electrophiles and nucleophiles? Very simple. So basically, electrophiles are those neutral species which are having electron deficiency, not in terms of charges but in terms of octet. We'll talk about them. Similarly, there are species which are having a lone pair onto the central atom and they can act as electron donating species. Now what about attraction? So if it is electron loving, it will be attracted to electron rich centers obviously, and the nucleophiles will be attracted to the electron deficient centers. Next, what is the reaction type? So the electrophiles takes part in electrophilic reaction. It's very simple to understand. So if the electrophiles are reacting, they will do electrophilic reaction, and the nucleophile will attack, then the nucleophilic reaction is taking place. The important thing is to classify them. So we'll try to classify them through some examples. You will try to get more and more examples and try to classify more and more molecules into electrophiles and nucleophiles. There can be cases where your same molecule can act both as electrophile and nucleophile. It's very obvious. Now, generally I told you that positively charged species are electrophiles. But if you take the case of BF3, it has a sextate, not a octet. Means it has only 6 electrons in the valence shell. As a result of this, it can accept electron because of its electron deficiency. Similarly, your AlCl3 also has 6 electrons in its outermost shell. Therefore, it can receive electrons from other electron rich species. What about nucleophile? So either they will be having a negative charge, like in the case of OH minus, Cn minus, Rc double minus, Cl minus, or it can have a lone pair on the central atom, like your NH3 has a lone pair. Similarly, your H2O has a lone pair. So they can donate those lone pairs and act as nucleophiles. Next and the last one is the movement of electron. How will the electron move from where to where? Still, we are not onto the resonating structure, but it is generally seen that electrons move from electron rich species to electron deficient species. So it's very obvious. So the one which is having a higher electron density will be the one donating that, okay, and the one which is having a deficiency of electron will be the one accepting those electrons. But the important part is that how they are shown. So we use curve arrow to represent the movement of electron. Here are some examples. You will get a more better idea about this example when you will study about resonance. But for now, you can think that there are two bonds on the left side of the Y and one bond on the right side of the Y. How you will show the electron movement from this left side to the right side? You will take the tail of the arrow, put it on the electron source where the electron is coming from, and move it on to the way where the electron is going. Okay. So here the pi bond is moving on to the adjacent bond position, and the arrow is having a tail on the electron rich position and a head on the electron deficient species. Similarly, the electron cannot directly move on to the next bond, it can move on to the atom itself. So here you can see the Y is receiving those electrons. Okay, again here the arrow is used to show the source and the sink where the electron is coming from and where the electron is going on to. Similarly, if your Y is already having an electron, it can donate onto further bond. So that is also a possible case. Here also the electron rich area is your 2 electrons which are present on Y, whereas the electron deficient is the single bond onto which the electron is going. Let us summarize all of this today's discussion. What are substrates? So these are those molecules that provide carbon atoms for the new bond formation, whereas the reagent are the one which are responsible for bringing about a chemical reaction by transforming a functional group or by introducing a functional group. Now in this process, two types of bond breaking can take place. First is symmetrical distribution, where each electron can get one electron, and that is called as homolytic fusion. The species that are formed are intermediates and it is called as radical. If the electron is distributed unsymmetrically after the fusion of bond, then we call it as heterolytic fusion. Okay, where both electrons are going on to one atom only and the other one is getting a positive charge. Here the intermediate that are formed are carbocation and carboanion. Then after we talked about electrophile. So these are electron loving species, often positively charged or neutral with electron deficient atom. And the nucleophiles are those which are having a negative charge, or if they are neutral, they will be having an electron pair onto the central atom. Thank you for joining the session. I hope you enjoyed it.